So hi, I will talk about some of modeling work I've recently done with Robin Wordsworth. We think for the first time we apply line-by-line radiative calculation in general circulation models. I will start from this figure, this infrared outgoing spectrum from some of planetary atmospheres. We can see some gases have very complex spectral features. And this is due to the rotational and vibrational transitions of molecular states. And if we can zoom in, we can actually see more complex features. This is a very big problem for climate modelers, because what climate model do, the GCM need the radiative heating and cooling rate to drive the motion of the atmospheres. So that means we need to integrate over the whole spectrum, and with this high resolution resolve these spectral features. This is impossible when people try to develop climate models in the last century. So what they usually do is to choose parameterizations. They usually separate this spectrum into broadband, like tens or 20s, and then do statistics. They study the statistical behavior of the broadband average opacities under different conditions. And develop the methods such as the band models and Curry distributions. And indeed, these methods guarantees rapid calculation in climate models, especially for Earth-like climates. But there are still problems. The model developed is not very flexible, especially if you want to change the partial pressure of the greenhouse gases or adding more species, or it has a complex vertical structure rather than well mixed in the atmosphere. The question we want to answer here is, since we have more powerful computation resources compared to the last century, the 1960s and 70s, could we use the line-by-line approach now rather than still use the broadband average results? And the answer is yes. To test this idea, first Robin developed this one-dimensional radiative convective model with the line-by-line radiative calculations, and he has validated it against a number of scenarios. For example, if the atmosphere is gray, it should be the same as the analytical solutions. And given the corresponding conditions, it can also generate Earth-like and Martian-like climate vertical structure. And another way to validate the model is to compare it with other models. So here I compare the PCM LBL with two others with two different ways to calculate radiative transfer. The LIFE is recently developed by Robinson and CRISP using a different way, like a root funding method to find the equilibrium profile rather than the conventional time-stepping iteration. And the CLIMA is a broadband model developed by the casting group. We have seen those two models in two of yesterday's talks. And those models are consistent in the lower troposphere. This is a 1-bar pure CO2 calculation. But in the upper atmosphere, the high-resolution model tends to be colder due to the strong cooling effect of the strong and thin, narrow CO2 lines. So Robin has used the model for a broad range of different kinds of climates. For example, the methane-rich atmosphere on early Mars, and even the post-runaway greenhouse atmosphere above the magma ocean. We have huge amount of water vapor in the atmosphere and surface temperature as high as 1,000 degrees to study the redox state of these planets. Then let's move to 3D models. I developed it based on the GFDL final volume dynamic core. This is a central part of all general circulation models which deal with the atmospheric transport and motions over spherical surface. Then to make climate models, we need 3 necessary ingredients. Well, actually, 2 of them are necessary. The part we want to emphasize is the in-stream line-by-line radiative calculation I just introduced. And we also have a convection scheme, which relaxes the unstable layer towards the neutral state. And there is also a boundary layer scheme that calculates the momentum energy flux exchange between the surface interior of atmosphere and the energy momentum dissipation in the boundary layer. The final volume cubosphere dynamic core is kind of different from the spectral cores people talk about in these days. First of all, the fun and volume method gives a more accurate calculation about the mass transport and energy transport as well. And the cube sphere horizontal grading schemes allow you to use more processors given the same horizontal resolution compared to the spectral cores, because you don't need to deal with the Fourier transforms along latitude circles. For the ones I'm going to show, I usually use 400 computation units, and actually you can use more. I chose 400 because our cluster is kind of busy, and many people are running runs about large eddy simulations and small-scale convections. So I usually choose 400, and there are 2,000 spectral grid points I used in the calculation. Then per hour, the model can integrate forward by 200 days. This is much faster before I work on this, actually. Then to validate this 3D model, we still compare it with previous runs. We choose this problem of atmospheric collapse on synchronous rotating planets because it's very simple. The atmosphere is pure single component, and the circulation is isotropic and only governed by a global overturning circulation. It's very easy to be compared with. And the result is consistent with previous models like the LMD model with different radiative and boundary layer schemes. A pure CO2 atmosphere collapses when the surface pressure is less than 0.1 bar given Earth-like conditions. And surface temperature distribution is the same, and this dotted area marks where CO2 condenses on the night side. And here I show the OLR. If you calculate the global mean and compare it with the absorbed stellar radiation of the climate system, the difference is 0.01 watt-meter squared. So I think this model conserves energy very well, and this is very essential for accurate climate calculations. Since this is a line-by-line calculation, I think it's better to show some spectrum calculated by it. And this is the outgoing long-wave radiation that is spectrum that is calculated internally and iteratively during the iteration. This is a substellar spectrum and antistellar spectrum. The difference of the two curves related to the thermal structure at these two locations. For example, if we look at the center of the 50 micron CO2 band, since CO2 absorbs so strongly here, all emission comes from the upper atmosphere. So due to atmospheric dynamics, there's little temperature gradient there, and we see no contrast between day and night side emissions. They are basically identical. And if we move further towards the shoulder of the CO2 absorption band, we begin to see some emission features on the night side. That's because we are penetrating deeper into the warmer interior of the atmosphere, and this emission peak corresponds to this maximum thermal altitude. And if we remove further, so I think this CO2 absorption 15 band maybe could be used as a good indicator to test thermal inversions in the atmosphere. And if we move further to the weak absorption regions, there are little CO2 continuum absorption here. We begin to see emission from the ground. On the day side is very hot and night side is very cold. So in this window region, we see the biggest contrast between day and night side hemisphere. So with these preliminary results, I hope I can convince you that the model we developed here could be used to tackle a broad range of climate problems and to be both accurate and flexible. So in the future, the next work we plan to do is to use it to simulate possible climates of an interesting exoplanet GJ1132b. It has Earth size, Earth gravity, and even Earth spin rate if it's synchronous rotating. So its orbital period is 1 day, and it's so close to the star, it receives 20 times more insolation than the Earth. So we would expect totally different planetary evolution here. It could be either CO2 dominated or O2 dominated if it has a large water inventory in its early history. The second work is kind of related to the first one. We could use it to study the abiotic oxygen buildup in a water-rich but temperate world rather than a very hot and warm state. And this scenario is this process is very sensitive to the upper troposphere condition near the substellar region, and therefore can only be accurately calculated in the 3D models. And the moisture dynamics is also quite different. We have done lots of work regarding it. It's totally different from Earth climate when water vapor, the condensable thing, only takes up a few percent. And we are also working on multiple scattering, which could improve the relative transfer calculation, and especially when you have hazes or aerosols in it. So about the exoplanet simulation, I'm still trying to figure out the appropriate absorption data to be used in it, because it's so hot, and there's no such measurement or calculation of the absorption cross sections. I can only show you some gray gas runs at present. So for this, although it's a terrestrial planet, because it's been so fast and so hot, you can see the climate pattern shows many similarity with the so-called hot Jupiters. And actually, it rotates faster than many of the hot Jupiters. This is the OLR map again. It's totally different from the CO2 map I showed you before. Both the crescent shape on the day side and cold gyres on the night side are related to the perturbation of planetary waves that are excited by the big thermal contrast between day and night side. And these planetary waves behaves very efficiently, transporting momentum from high latitude towards the equator, and therefore we see this superrotation jet and the two high latitude subrotation jet. If you look at value at color bars, it's 200 meters per second. And this is a long-term mean and zonal mean. If you look at the instantaneous wind speed given specific locations, it can reach 500 or 600 meters per second. I believe it's much faster than many of the wind speed in the solar system observed. Okay, I will stop here and take questions.
So we have time for a couple questions.
Does your code go out into the shortwave? And if not, is it feasible to extend it out that far if you want to do things like lava planets?
Yes. The short-wave calculation is basically the same as the long-wave calculation, but currently there's only absorption in it. I said we want to implement multiple scattering later. We only have really scattering in it now.
But is it going to slow it down a whole lot if you need to extend out your wave number grid from 0 basically all the way to like 30,000?
That's a good point. But currently we choose the same grid points both for long wave and short wave. So same grid points means a low resolution in the short wave compared to the long wave. You're right. When I say the running times, it includes both the short wave, long wave calculation. And definitely you can increase the spectral resolution for the short wave. Could slow things down a little bit, I think.
So I can imagine the line by line being super useful for people who want to do high dispersion spectroscopy. But the other way to do that is just to run something using correlated K or whatever, and then just post-process it to kind of mimic high resolution data. So in what, I guess, can you give us a sense for what sort of planets would that be a horrible approximation? Like in what situations will that give like just totally a wrong answer to post-process for high resolution instead of doing it line by line like you're doing?
So the limitation I think about correlated case, we don't know when it becomes inaccurate. For example, the RTMG, definitely we can not use it to simulate the Archean time when you have high CO2 concentration. That's why we think we need to go back to the high resolution calculation instead of using any parameterizations. Because if you change the gas conformation, the parameterization, you also need to, the safe way is to reparameterize it. First, it's very time expensive. And second of all, you still need to compare it with line by line calculation eventually. So we think why not we start from line by line directly rather than to do any parameterizations.
We have time for one more question.
Interesting talk. So my impression is that even if you run the whole Hadron database line by line for one layer, it will take, for that spectral range, it would take you 1 hour. So I'm just want to say that typically when you make it line by line, you're actually making cutoff for intensity. So you are actually removing a lot of the lines that you think are not relevant for the transfer. And that actually, that's what I prefer actually to do correlated K. Correlated K with all the caveats it will, if you run it a priori, you will also include the weaker lines that you typically would not include in this approach. So even though correlated K has some caveats, my impression is correlated K is actually better than line by line for computing this type of things. And there's a new line of work being investigated right now called supralines. So now when you have like something like billions of lines, they want to transform a lot of lines into an average line, and that you synthesize one line for that spectral range. So it's like a correlated K mixture with line by line. And I think if you want to include billions of lines, that is probably the way to go then use line by line.